Hi there, everybody. We're going to do the best we can. I'm going to go over some of the material from the beginning of Unit 6, and then we'll talk about some things in 6.2. I believe we got through some of the exercises in 6.2, but it's been a little while, so I'm going to do a little review of what's in 6.2, and then we'll talk about 6.3. And I'm also going to give you an assignment to do at home. And I think it would be a good idea if you could take a photo of the assignment after you do the assignment, take a couple photos and email them to me so I can look them over. I'm not going to make this mandatory, but especially since we're not in class together to go over the exercises, I think that it would be advisable for you to not only do the exercises, but also take a couple of photos of your exercises and email them to me so I can look them over to make sure that you're doing them correctly. Again, it's not mandatory, but I think it would be a good idea, certainly would be advisable. So let's go over a little bit of the truth tabular definitions of our logical operators that are in our language. I have a few of them on the board, not all of them, but for example, the easiest one in a way is the negation. What this table is telling you is that for any formula, let's call it P, whatever formula P is, there's going to be two possible combinations, or there's going to be two alternatives about whether P is either true or false. And if P is true, that means not P is going to be false. So notice that the F is written underneath the tilde, right? If P is false, then not P is going to have to be true. Okay, and basically that's just what we mean by saying not the case. When you say something is not the case, you're saying that whatever the truth value of that statement was, I'm denying that. So whenever P is true, not P has got to be false. Whenever P is false, not P has got to be true. Now this is just something you have to memorize, but it's pretty simple. Here's the definition. Again, I call this the truth tabular definition of conjunction, the dot. I hope you can see the dot there. So when you have two formulas, whatever they are, let's call them P and Q. So there's going to be four possible combinations. Either they're both true, the first one's true and the second one is false, the first one's false and the second one's true, or they're both false. So those are all the possible combinations for P and Q. And then notice that here you have the truth value of P and Q. When P and Q are both true, the conjunction is true, right? But if one of them is false, and certainly if both of them are false, then the conjunction turns out to be false. So again, this is giving you the result. The truth tabular definition of the conjunction is when either one of these are false, the result is going to be false. It's only going to be true on the top case. All right, and then we have over here, we have the disjunction or the wedge. So again, with P and Q, there's four possible combinations. This is the standard way of listing the possible combinations, T, T, F, F, and then alternating T, F, T, F. And the disjunction is going to be true as long as one of the two disjuncts is true. All right, it's only going to be false on the bottom. When P is false and Q is false, then you're going to have P wedge Q is going to turn out to be false. Okay, so you have to memorize this. It's not that hard. That's basically what the word or means, used in the inclusive sense of the term or. Okay, now the other, there's a couple more connectives or logical connectives. We'll just list those on the board. We've got also the horseshoe and then the biconditional. So let's just quickly go over those two. I guess I'll save my possible combinations over here. If we have P horseshoe Q, P horseshoe Q, so the rule is that it's going to be only false on the second case, because this is saying if T is true, then Q also is true, but here Q is false. So On this row, the horseshoe turns out to be false, and by definition, we're going to say that it's true otherwise. It's only false when the antecedent is true and the condition and the consequent is false. All right? This is just something you have to, again, memorize. And then we have the biconditional. So you're going to have PQ, two possibilities. There's going to be TTFF, TFTF, and the biconditional P biconditional Q is going to be true whenever they're the same. Because the biconditional is essentially saying that whatever value P has, Q has. So if that's going to be true, that means they have to have the same value. If they're both false, that's fine. It's going to be true on the top row and true on the bottom row, and it's going to be false on the second and third rows. So that is the definition of the biconditional. Okay, again, this is review because it's been a while since we've been doing these things. Now, if you look at exercise 6.2, we're going to look at exercise 6.2. I know we did our Roman numeral 1 already. This involves identifying the major operator of a formula. So I think you guys know this, but I'm not sure. I'm going to just do a couple of examples of 6.2 number 1, Roman numeral 1. I guess if you already know this, you can just speed through this video a little bit and get to where I start talking about 6.3 at some point. But just to quickly go over the idea of a major operator, I'll do just a couple of examples. Let's say we have, looking in my book here, we've got, this is number 2, G dot P, horseshoe, not H, wedge, not W. Well, that's inside a parenthesis, wedge, not W. Okay, so this is again number 2 from Roman numeral 1 at the end of 6.2. G dot not P horseshoe, tilde, parenthesis, H, wedge, not W. So I'm asked, what's the major operator? The major operator is going to be the operator that holds the whole thing together. So the dot is not the major operator. This is holding the G and P together. And this wedge is not the major operator because that's clearly holding the H together with the not W. And so the tilde is not the major operator. What about this tilde? This tilde is governing that formula, or that part of this whole formula. So in the end, this is the MO. The major operator is that horseshoe over here. Okay, I'll do another example. Let's try number 6. Number 6 is, let's see if I can get this right, tilde, then we have a bracket, parenthesis, P dot, not R, horseshoe, parenthesis, not E, wedge, F, bracket, right bracket. Okay, so with this formula, again, the method sometimes used, it's called pairing parentheses. Pairing parentheses means, what does this bracket go with? Well, these two parentheses clearly go together. In other words, the inner parentheses go with the next most innermost parentheses. So these parentheses go with this. These two parentheses group this one. These two parentheses over here group this thing. So anything that's in here is not going to be the major operator. It's either got to be the horseshoe or it could be the tilde, okay? Which one is it? Well, the brackets clearly are connecting this whole thing together, and that whole thing that's inside the brackets is being negated by this tilde on the outside. So the correct answer would be that the tilde hanging out on the left side here is the major operator. It's the thing that governs the whole formula, as it were. if you were constructing this formula from the simplest parts, you would put together the P and the not R, the not E wedge F, then you unite that with a horseshoe, put that in a big brackets, and then add the tilde on at the end. So the tilde is the major operator. Now again, I believe we did these in class. Just going over it, if you have any trouble identifying major operator, then I suggest that you do some of these exercises, see if you can figure it out, and email me your results, and I'll try to help you out. Now let's talk about Roman numeral 3. Okay, Roman numeral 3 in 6.2. 6.2 Roman numeral 3. You're given certain formulas and you're told that the components have certain values, right? So if you look at 6.2 number 3, you're given that A, B, and C are all true, whereas X, Y, and Z are all false. And then you have to compute the value of a given formula. So let's just do a couple of those. And again, if you think you know all this, you can skip through this. I just wanted to refresh our memory about how to do these things, because if you can't do 6.2, you're definitely going to have trouble with 6.3, because things kind of build on each other going forward. So let's take, B dot not Y. We're given B and not Y. We're told, we're given that Y is false and B is true. So I need to compute the value of B and not Y. Well, you work from the most simple components and build up until you get to the major operator. So I'm going to know that not Y is going to have to be false, because remember the tilde reverses whatever the value of Y is, not Y is going to be false. So now I have T and T. The value of a conjunction is going to be true when both components are true. So the answer to this would be it's true. If B is true and Y is false, that's what we were given, then B dot not Y is going to have to be true. Now, of course, that was a simple, relatively simple example. I'm going to do another one. I'm going to pick number 14. Again, this is 6.2, Roman numeral 3. And I'm looking at number 14, and that is, let's see, I've got not X wedge, not B, and not Y wedge A. Okay, that's number 14. Not X wedge, not B, and not Y wedge A. Okay, now remember I'm given X is false, B is true, Y is false. Now notice how I'm again listing the value right underneath the component. Now, what should I do first? Well, again, I have to work from the simplest components outward. So let me do not B first. So not B is false. And then I get X wedge, not B is going to be F wedge F. So this is going to be false because the value of the wedge is false when both are false. Here I need to do the tilde Y first. This is true, and now I'm looking at something that's true, wedge something that's true is going to be true. Okay, now what should I do next? I've got the dot here, but I also have the tilde here. Okay, well, the tilde over here doesn't govern the whole thing, right? It only governs the X wedge not B. So I'm going to say that tilde this whole thing is true, and then I have T dot T, which is also in the end true. Okay, because tilde this whole thing turned out to be true. The value of this thing is true. So now I have T and T. So the answer is, okay, I'm sorry, this is below the screen. Sorry about that. The answer over here, to make it more visible for you, is that this whole thing is true. The result is true. Okay, so you need to know how to do this exercise in order to be able to get to master 6.3. So if you're having any trouble or you're unsure, I suggest you do the exercises in 6.2, Roman numeral 3, take a picture of them, and email them to me, and I'll check them over and see if you're doing them right. If again, you don't need to do this, but if you feel you want to, you're certainly welcome to do so. Okay, now we're going to talk about, and of course, if you have any questions, you'll have to email me. You can also call me on the telephone. You know, there's only 5 students in our class. If you want to speak to me on the phone, go over some exercises orally over the phone, then that would be fine. And again, my number is 548-9542. All right, okay. So let's talk about what's going on in 6.3. I don't believe we got to 6.3 yet, so let's talk about that. Now, what you have here is truth tables for propositions, and you're going to learn sort of a way of classifying or categorizing certain propositions depending upon what happens when you do the truth table for the entire formula. Okay, let's start with something that is called a tautology. All right, a tautology. A tautology is a formula that has to be true. It's a statement that must be true no matter what the values of the components are. That may sound a little surprising, but I'll give you an example of a tautology, and then we'll give you the more formal definition of a tautology is, well, it's basically a statement that always comes out true on every single row of the truth table. It ends up with a T. So let me give you an example of this. Let's suppose, here's a very simple one. P or not P. Okay, actually Aristotle, I think it was Aristotle who called this the law of the excluded middle. Anyway, don't worry about that. The point is, P wedge not P says, for any statement, either it is true or it is not true. Well, given in our system of logic, we only have 2 truth values for any given possible statement, then this is going to have to be always true. And this can be proven. This is the nice thing about the truth table method, that you can demonstrate that this is a tautology. All right, how would you do that? Well, to do a truth table for this formula, what you do is you make a cross, which is always a nice thing, like so. And then you list the components that are in this formula. There's only one component, namely P, right? So there's only one component, the component is P. And now you put down over here all the possible combinations of truth values for P. There's only 2, right? P is either true or it's false, okay? So now you're going to compute the value of this formula if P is true, and you're going to compute the value for this formula if P is false. So let's plug this through. When P is true, I'm going to write, this is now just writing the T under the P. When P is true, we know that not P is going to be false. T wedge F is true, right? Because this is a disjunction. So on the top row, P wedge not B comes out true. Now on the bottom row, when P is false, okay, well, P is false here, P is false here. Not P is true, so you have F wedge T, T is also true. So this over here indicates that no matter what the value of P or Q is, P wedge not P comes out to be true, and that is what is called a tautology or a tautologous statement. A tautologous statement or a tautology is a formula that always comes out true under the major operator on every single row of the truth table for that formula. So that is a tautology. Now, there's more complicated examples of tautologies, okay? Let's see. Let's give you a little more complicated example of a tautology. Okay, suppose you have something like, let's say P and Q horseshoe P. Okay, I happen to know that this is a tautology. I mean, if you think about it, it's logical. But this is saying if P and Q is true, or are true, if P and Q are true, then P is true. So that should always be true. I can demonstrate that that's a tautology by doing a truth table for the whole thing and showing that under the major operator, it's always going to come out true. Let's try to do this. We make a cross. All right. I'm going to list in alphabetical order over here all the components that are in here. There's only P and Q. For P and Q, the possible combinations are as follows. And again, this is the standard way of writing out your truth table. T, T, F, F, T, F, T, F. That way you're sure you have all the possible combinations for P and Q. And now you're going to look at this, and you're going to say like this. Well, P and Q is going to be true here, and remember it's going to be false, 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 because P and Q is only true when both components are true. Now over here, the value of P, I'm just going to copy over from here the value of P. It's T, T, F, F. And now the major operator is the horseshoe. So again, with the horseshoe, the only time your horseshoe is false is when the antecedent is true and the consequent is false. Here you have TT, so it's true here. Anytime the antecedent is false, we're going to say that the horseshoe is true. So that means you've got exactly what I was telling you before. This formula comes out true under the major operator on every single row, thus demonstrating that this formula is a tautology. So you're going to have some of these examples on the final exam. I'm going to give you some statements. You're going to have to do a truth table and determine, is it a tautology or is it something else? What else could it be? There's two other possibilities. So, but I'm finished showing you, I showed you a couple tautologies. Another kind of statement is what is called a contradiction, or a better term in my mind would be a, well, the book uses the term a contradictory statement, or I would say self-contradictory. A self-contradiction is a formula that always comes out false under the major operator on every single row for the truth table for that formula. So let me show you an example of a contradictory statement. I'm going to use this framework here because, let's see, thinking of a contradiction, something that has to be false would be, how about something like P, horseshoe, not P, and not Q. Okay, I think this is a contradiction because what this says is if P is true, then it's also true that not P and not Q are true. And I don't think that can be the case. If P is true, that can't imply that not P is also true. I'm hoping that this is a good example of a contradiction. Let me see if I'm right. Again, to do the truth table, I go T, T, F, F. I'm just writing out the value of P, copying it over literally from here. Not P is going to be the opposite of whatever P is. F, F, T, T. All right? And let's see what we have over here. Not Q is going to be, I think I made a mistake. F, T, F, T. So, see, I'm actually going to be wrong here. This is not a contradiction. I made a mistake. I thought this would be a contradiction, but my truth table is showing me that actually Well, we'll see what happens here. This is, let me sure I did this right. Not Q is FT, FT. The conjunction is F, sorry, F and T. This is the value of the dot. And then when I go over here, I get F, T horseshoe F is false, T horseshoe F is false, but F horseshoe F is true, and F horseshoe T is true. So lo and behold, I was wrong. I thought this would be a contradiction, but actually it's not a contradiction because it's possible that the statement could be true. When is the statement true? When you have, when P is false. If P is false, the whole horseshoe, God, I should have known that, right? Whenever P is false, the horseshoe is going to turn out to be true. So this is not a contradiction. This is what we call a contingent formula. This is a contingent formula. The word contingent means it sometimes comes out false and sometimes comes out true. Or if there's one case where it comes out false and at least one case where it comes out true, we're going to call it a contingent formula. A formula that is not necessarily false. It is not a self-contradiction. Because if P is false, then this whole statement turns out to be true. I know what I was thinking of. I bet you, here's an example of a contradiction. If we change this, well, let me give you a different example of a contradiction. Okay, let's just think of a different example of a contradiction. Let's take something like, let's do something a little more complicated. Suppose you have P and Q biconditional, not P and not Q. Okay. I think this is going to come out to be a contradiction. I hope so, because I'm thinking this is saying P and Q is equivalent to not P and not Q. That sounds to me like a contradiction. So again, a contradiction is going to be a formula which comes out F, 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 F. Let's see if I'm right. Again, I'm just using this again because this has the possible, all the components are P and Q listed over here. All the possibilities are listed over here, T, T, F, F, T, F, T, F, right? Now I'm going to plug through, first do the conjunction. It's going to be T, F, F, T, oh sorry, T, F, F, and F, right? The dot is only true on the top row where both P and Q are true. Now, not P and not Q is going to be all of the values of P and Q are going to be reversed. This is going to be FT, FT. This is going to be FFTT. The dot is going to be false, 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 true. Right? This is the value of this conjunction. And this is the value of this conjunction. Now, for the purposes of finishing this off, we're going to look at the value of the biconditional. Remember that the biconditional is true whenever they have the exact same value. It's going to be false when they have a different value. So TF, the value of this becomes false, right? False. And here again, look at this. It's true over here. It's true over here, and it's false over here. So again, I failed to find a contradiction. Mystified. I thought this would be a contradiction. It sounded to me like a contradiction. But when I do the truth table for it, I find that it is possible that this whole thing could end up being true. whenever the first is true and the second is false, or whenever the first is false and the second is true. So I have to say this is not a contradiction, this is a contingency. Sometimes comes out false and sometimes comes out true. So this is the value of the truth table method. Something that I thought was a contradiction when I tested it turned out to be a contingency. Amazing. We gotta find a contradiction here. Okay, there's gotta be a contradiction somewhere in the world. So let's, you know what? I'm gonna get very blunt here and give, this has got to be a contradiction. What I show you next must be a contradiction. Very simple one. Look at this. I'm going to go P and not P. Right? That better be a contradiction. This is saying P is true and it's also not true. There's no way that could be true, right? So let me test that out. We'll see if this is a contradiction. I think I'm right this time for a change. Make a cross. The only value here we have, or sorry, the only component we have here is P. It's going to be either true or false, right? So here P is true, here P is false. Not P reverses the value, FT. So now I'm going to do the conjunction, the final operator, T dot F is false, and F dot T is false. So, wow, I came up finally with a contradiction. It's a formula that only has one component. There are contradictions with in formulas that have more than one component. As your book gives you several examples of those, I'm looking down in the book, sorry. Let's see here. Where's an example of a contradiction in the book? I'm actually not seeing one. Well, here's one. Here's a contradiction. Let's take a look at this one. I think this is what I was trying to get at earlier, but let's try this statement. I'm going to switch it up a little bit from what's in the book. P wedge Q, biconditional, not P and not Q. Okay, this should be a contradiction because, well, I think it's a contradiction because that's what the book says, but also because, look, P wedge Q says either P or Q is true. This says P is false and Q is false. So these two statements cannot live together in the same world, so therefore they're not equivalent. Well, this is saying that they are equivalent. Let's do a truth table for this. We have two components, P and Q. We make a cross. We put down the values of the possibilities, T, T, F, F, T, F, T, F. P wedge Q. Let's do that first. It's going to be true in all cases except for the bottom one. Now, not P and not Q. I'm going to make it easy for myself. I'm writing the value of not P and the value of not Q. I need to do this dot. So I have F dot F is false. F dot T is false, false, this is true. So this is the value underneath the dot. This is the value underneath the wedge. Now I look at this biconditional. It's going to be true only when the values are the same. So I have false, this is false, this is false. this is false, and this is false. So there you go. This would be the final answer. Sometimes it's just good to indicate that that is the final answer by, well, what you're doing is you're showing that this is the major operator. This is the result for the entire formula on each row. It always comes out false, 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 and false. I'm talking about this one here. And so this is a contradiction or a contradictory statement. Okay, so there's three types of statements. Tautologies always come out true. Contingencies, there's at least one true and one false result on the truth table. And then you have contradictories, which are completely false all the way down. Now, there's another thing that's going on in 6.3. It's called comparing statements. So here what goes on is you're given two statements, two independent statements, and you have to do the truth table for both of them, and then you compare them and see when do they both come out true, when do they both come out false, can they both be true at the same time? So there's going to be a classification for pairs of statements. Okay, your book explains that comparing statements, you're going to have a couple, actually 4 possibilities. Okay, if you look on the last, more or less the last page in 6.3, you can have two statements that are equivalent. Logically equivalent means those two statements end up having the same value exactly on the truth table. You could have two statements that are contradictory, which means that whenever one is true, the other's false, and whenever one's false, the other's true. You can have statements that are consistent, which means that they don't have the exact same pattern on the truth table as a result, but they can both be true. That's consistent. And then you have inconsistent, two statements which they don't have the exact opposite truth tables, but they never come out both true. Okay, so basically if you look at the examples, I'll go through them on the board if you like. Again, if you want to speed through this, if you feel you don't need to listen to this, that's fine with me. But let's just try a couple of these out at least. Again, here you're given pairs of statements. You're given two different statements, and you are asked to compare the truth table for each statement. So let's try, I'm just going to use the examples that are in the book. If you have, let's say, K horseshoe L, and you're given not L horseshoe not K. Two different statements, but what you could do is you can write them on the same truth table like this. Just keep a space in here, indicate that these are two different statements. Then you would list the components in alphabetical order, so HIJKL, so you have K and L, there's going to be TT, FF, and then there's going to be TF, TF. You're going to do the value for K horseshoe L. That's going to be false only on the second row, otherwise it's true, right? So this is the value for the horseshoe. Now I go over here. Not L is going to be F, T, F, T. It really does help, by the way, to use lined paper when you do these exercises, so you don't get, messed up on your rows. Not K is going to be F, T, F. Excuse me. It's going to be F, F, T, T. Okay, because remember, you're looking at not L, and this is K over here, so not K is going to be opposite of these values. Okay, now you're ready for this little horseshoe in here. This is going to be false over here, otherwise it's going to be true. The horseshoe is only false when the antecedent is true and the consequent is false. So this is the value underneath the horseshoe. This is the value underneath this horseshoe. Now I compare them. What do I see? I see that T, T, exactly the same. F, F, exactly the same. T, T, exactly the same. T, T, exactly the same. What does that mean? It means that these two statements are always going to have the same truth value. No matter what K stands for, no matter what L stands for, these two statements will have the exact same truth value for every single possibility of whether K is true, L is false, or whatever the combination of K and L are. So that means I'm going to say that these two statements are logically equivalent. Okay, a pair of statements is logically equivalent when they have the exact same pattern of truth table on every single row of the truth table. Didn't say that very well, but you get the picture, I hope. Okay, and then, so the other possibilities are contradictory. It could be that you end up with two statements that have the exact opposite values. Let's show you that one. Again, this is illustrated very clearly in the book, but I'm going through it. You have, let's say, K horseshoe L and K and not L. Okay? It should be contradictory because this says if K is true, L is false. This says K is true and it's not the case that L. So this should be a contradiction. Okay, for K horseshoe L, you get T, F, T, T. For K dot not L, I'm going to write the values over. T, T, F, F. Not L is F, T, F, T. The dot is going to be true only here. False over here, false and false. So the major operator comes out like so. Now I compare the major operator for K horseshoe L on every single row. Whenever the one's true, the other one's false. Whenever this one's false, this one's true. True, false, true, false. So therefore, we're going to say that these are contradictory statements. Contradictory statements. Okay, and consistent, that's the next possibility, is you could have two statements where they're not completely different. Maybe I'll just ask you to look in the book for this one. If you look at this, look in the book, you got K wedge L. I'm on the last page, or almost the last page of 6.3. So you have K wedge L, then you have K dot L. So you're going to see that K wedge L comes out TTTF, and K dot L comes out true on the top and false otherwise. So what happens here is that K wedge L and K dot L are consistent. They could both be true. It is possible that K and L is true and also K wedge L is true. When would that be? When both K and L are true, then K wedge L and K dot L are both true. On all other, and then there's also a possibility that they come out false. That's on the last row. Okay, and then in the middle, they come out opposite. So there's at least one row where they come out true. That means we call these statements consistent. Finally, inconsistent, let me do this one on the board. We have a case of an inconsistent pair. We have K biconditional L, and we have K dot not L. Sorry, I'm looking down to look at the book. K dot not L. Okay, again, to illustrate that these are inconsistent, we put them on the same row over here, list the components, K and L. These are the possibilities for K and L. K biconditional L is going to be true when the value of K and L are the same. And then you have F over here, F over here. K dot not L is going to be T, T, F, F, just copying over the value of K, which you really don't have to copy over the value of K. I'm just doing that because it just makes it easier to see. It's a little slower, but not L, I'm just going to go F, T, F, T, the opposite of L. Now I do the dot here. This is false, true, false, and false. So the value of K dot not L is like so, F, T, F, F. And now I compare that with the value under K biconditional L. What do I see? That, well, whenever this is true, this is false. Whenever this is false, this is true. So far, it's looking like it might be a contradiction. But this is not a contradictory pair. Why? Because here, they both come out false. So that means that there's at least one row where they have the same truth value, which means that they are not contradictory. May sound a little bit odd, but the definition of a contradiction is that they have to have the exact opposite pattern, and here they don't have the exact opposite pattern. However, what we do see here is that there's no row on the truth table where they both come out true. So that means we're going to say that they are inconsistent. Inconsistent. This is an inconsistent pair. Inconsistent means they can't both be true at the same time, even though they could both be false. At least on one row, they do come out both false. So the skill that you're expected to master in 6.3 is basically to be able to take a formula, determine whether it is a tautology, a contingency, or a contradiction. Or take two formulas and determine their relationship. Are they consistent? Are they equivalent? Are they inconsistent? Or are they contradictory? So what I'm going to ask you to do for homework is Roman numeral 1 and Roman numeral 2 at the end of 6.3. You do not have to do, at this time, Roman numeral 3 from 6.3, which gets into translation, and that's a different skill. So I'd like you to focus on the skills that we've been trying to master today. Again, it's exercise 6.3, Roman numeral 1. Try to do all of them. Roman numeral 2, try to do all of them. Now, if you can't do all of them, you don't have time to do all of them, then at least do some of them. And you may, again, take a photo of your work and email the photo to me, and I'll look them over and see how you're doing. So I think that's enough for today, and try to get me your homework in sometime maybe by Monday or Monday afternoon, and I'll look them over and try to give you some feedback. And then next Tuesday, I'm going to do a little video on 6.4. Be well. All the best wishes to you. Stay healthy.